So let's just get into it, right? So you've probably seen chemical reactions before. And what a chemical reaction is, it's basically just the rearrangement of atoms to make new molecules. That's all it is. And we talked about this when we talked about chemical changes. It's basically just the concrete description of what kind of chemical change happens. And you have reactants to products. So the reactants are going to be on the left side. The products are going to be on the right side of whatever chemical equation we're looking at. So you can see an example there where octane and oxygen make carbon dioxide and water in an engine. Move my camera out of the way. Yeah, an engine. Cool. So basically, you're making new substances. So, and also the elements are conserved. So they're just rearranged. That's it. All right, so here's an example of a chemical equation. You have the combustion of methane. It's the all right, I'm here. So my internet disconnected. I'm sorry about that. I hope it doesn't happen again, because this happened during the ending of the test where my internet disconnected a couple times. Oh, shit. All right. I'm sorry. This is the new apartment problems. Everybody still there? Yeah. Okay. So if you hear me stop talking again, it's probably what happened. Okay, good. All right. So of all times, like It's got to happen now when I'm doing this. Yesterday was all good. Oh, okay. Anyway. So you have a chemical reaction and your you have the coefficients in front. These coefficients.
We can't see his slides.
What's up, Santiago?
I can't see his slides.
There's lag.
I can't see the slides.
Oh, you can't see the slides. Oh, okay. Let me start the screen share again. Okay, now you should.
Yep.
Okay, cool. Thank you. All right. So you have the coefficients in front of the reactants and products. These coefficients basically mean the amount that you need with respect to the other molecules to make the reaction have the follow the law of conservation of mass, law of conservation of matter. Meaning, if you didn't have these coefficients, right? If you had CH4 plus O2 and this reaction without the coefficients, you would see that you'd have H2 on the left side, on the right side, and you'd have H4 here. So there's no possible way that you can have a reaction with 4 hydrogens on the left and only 2 hydrogens on the right, unless hydrogens were removed. And with the oxygens, you can have 2 oxygens on the left, and then it would be 3 oxygens on the right, which wouldn't make any sense either, because you can't just randomly gain oxygens in a closed system. So that's why we have these coefficients to show us how are the reactants molecularly behaving, how many molecules react with how many molecules of reactants in order to make a full chemical reaction where everything is conserved. So also the G, so there's 3 different states, or 4, that there's actually 4 different states that we're going to be talking about here. And where are we at? So we're here. So in this chemical reaction, you see G, right? That means gas. There's other ones. There's S, which means solid. There's L, which means liquid. Also, there's one that you're going to see more often is AQ. So AQ means aqueous. Aqueous. Nope. AQE, yeah, aqueous. So this is aqueous. So an aqueous solution, that means it's in water. It dissolves in water readily. So if you have a 0.5 molar solution of NaCl, that would be an aqueous solution. It wouldn't be considered a liquid. When you say something is a liquid, it means it's a pure substance. It's a liquid. So if you have water liquid, that means it's only water, and it's deionized water. There's nothing else in there but water. So that's what they mean. And then you have your coefficients. So when we balance these equations, we're going to be adding coefficients that correspond to the correct number of molecules to react and to balance out the equation, meaning the coefficients make the left side of the equation and the right side of the equation have the same number of the same type of elements. That's basically what balancing equations is and why we do it, to conserve from the left side to the right side of the equation. So there are many different ways to balance equations. People teach in textbooks and also in high school, maybe you learn to write a chart. You write a chart with the different elements going down, and then you write on the left side of the symbol a number, and you cross it out, and you write on the right side, whatever. I don't like that. I think it's too much work. There's an easier way to do it. So I'll show you how we got this. Now, this is a fairly easy one to balance. So let's just look at it from left to right side. You have HGO makes Hg plus O2. So the way I would balance it is you just look at it and you read it like a book. You read it from the left side to the right side. And you look at each element and you just see if the left is equal to the right. So let's look at it. Hg, there's one here. Hg, there's one here. Can you please mute your microphones? It's not muted. I do hear people. I can't tell whose is. They all seem muted. Is that me? It's not me. No. All right, I'm going to mute everybody. Okay. All right. Anyway, so what I would do is look at the first element, Hg. There's one here, there's one here. All right, cool. Next element, oxygen. There's one here, there's 2 here. So that means you have to put a 2 on the left side. So a 2 would go here. Then let's reread it again. So you go every time you change a coefficient, you basically reread the equation. And if you get really good at this, it doesn't take too much time. So you put a 2 here. Now there's 2 Hg. Oh, only 1 Hg here. Put a 2 there. And then you end up with that. So it's a very simple example. Now we're going to cover a lot of examples. Here's one of them. So you have glucose reacts with oxygen to produce gaseous carbon dioxide and water vapor. So let's do this exact same approach. And I'm going to do it with using the pen this time. So let's look at carbon. There are 6 carbons here. Carbon 6, C6. Let's go on the right side. There is 1 carbon. So that means you write a 6. H12, there's 12 of them. H2, there's 2 of them, all right? Another 6, because 6 times 2 for hydrogen is 12. Oxygen, on the entire left side, there is 6 plus 2, which is 8. Let's look at here. There is 6 times 2, which is 12, and here there is 6 times 1, which is 6. If that's the case, that means there's 18 total. Now here we have O6 and O2. Now this is where this is one little thing where it gets a little complicated, but if you're good with numbers, it should be not too bad. So you have 6 here, and you need some multiple of 2. So you have some multiple of 2 to add up to 18. So if you look at this 18 on the right side, and let's say this 6 cancels out, whatever, you have 12 left. So you need 2 times something to equal 12, basically is what I'm trying to say. And if you put a 6 there, it works perfectly. So you do 6 times 2 is 12. You have 12 oxygens here. And then you have 6 of them here. Add them up, that's 18. On the right side, you have 6 times 2, which is 12. And then 6 over here, which is 18. So that is how you balance equations. This is a intermediate one. It's not easy, but it's not hard. So is there any questions on that one? So basically, you're just putting the coefficients in order to have the elements have the same number of atoms on the left and right side. Okay, then let's keep going forward. All right, so now doing these chemical, let's do one more. Do we have another one? Or we're going to be doing them as we learn more about them. But yeah, let's do one more. I feel bad. I want to do one more. All right, so let's do one that involves polyatomic ions, because we learned about them, and also the rules are the same, but it's a little bit, there's a little bit we should know. So let's do MgOH2. This is a base, magnesium hydroxide. It's a strong base. And then let's add to it Na2. Yeah, Na2SO4. No, that wouldn't work. Let's do here we go. Na3, make it complicated. Na3PO4. So when this reacts, this is called a double displacement reaction. And it will create magnesium phosphate, which will be Mg3PO4 plus NaOH. So basically what happens is, you can see what happens in the reaction. That's a nice O. You can see that basically the cations and anions switch. So if you switch the magnesium with the sodium, you get this product. So you can take a look at that. You see they switch. And we'll be learning about this type of reaction when we cover the different types of chemical reactions. Okay, so let's take a look and use the same exact approach that we were using for the previous examples in balancing. So let's look at magnesium. You have 1 magnesium here. You have 3 magnesiums here. So we're going to put a 3 there. Let's use a different color. We're going to put a 3 here. Now, based on what I just said, you would say, oh, let's look at oxygen. Oh, no, there's 2 oxygens here, 4 of them here. Oh, no, it's complicated. What do I do? And there's 2 sources of oxygen over here. Don't look at it that way. Whenever you have polyatomic ions, always look at them as their own entity. So look at the ion as a packet. Look at it as a new element. So your phosphate is its own thing. The phosphates are their own thing, and the hydroxides are their own thing. If you see the same polyatomic ion in the left and right side of the equation, then you can do this. Sometimes the polyatomic ion might split up. In that case, you can't do it. But most of these equations are the polyatomic ion is going to be conserved in the left and right side. So now that we know that, we can go through and we can see hydroxide as a whole. There is 2 of them. Let's look at the right side. Hydroxide as a whole, there is only 1. This means we could put a 2 there. Going forward, Na3, there's 3 NAs here. Here, there's 2 NAs already. So this means we have to change the coefficient. So if you have 2 NAs here and 3 NAs here, you could just say, oh, we'll make this a 3 instead of a 2. That wouldn't work because that would conflict with what we first did with our hydroxides. So this 2 stands, and we just need to make the common, we just need to figure out the least common denominator between 2 and 3, which we know is 6. So if we put a 2 here, meaning 2 times 3 of the sodiums is 6, and we turn this into a 6, so I'll do that. And by the way, if you lost me, this is a very complicated one. So if you understand this, you're good to go. But I'll explain it and take questions when I'm done. So if you put a 6 there, you see how it all works out, where you have 2 times 3 sodiums, 6 sodiums. That's good. Sodium's good. Hydroxide now, 6 times OH. You have 6 OHs. Here, you have 3 OHs. You have 3. Oh, yeah, wait. Oh, you have 6 OHs. Oh. Okay, let's start over because we ended up with the right answer, but I skipped a step. So let's do that again. Magnesium 1, magnesium 3, 3. I didn't forget the 3 was there. So hydroxide, OH 2, 3 times OH2. That's 6 of them. So you have 6 OHs, 1 OH, 6. Now that works out. Sodium 3, sodium 6. Put a 2, done. And let's look at the other one that we didn't touch. We have this one. We have 2 times 3, or we have phosphate. 2 times PO4, PO4 2. Magnesium 3 times Mg, Mg 3. All good. So hopefully that one, the second time I explained it, was a lot better. But basically all we're doing is going through the elements as they appear in the equation and writing the coefficients as such. And that's really as complicated as it gets. There is one next level to it where sometimes it's not as obvious and there's different sources of the different elements and it gets weird where there's multiple sources, but there is still ways to figure that out. And we'll do those examples at the end or soon, sometime soon. So yeah, is there any questions right now? And I'll look at the chat window. Any questions? Seems pretty straightforward, hopefully. But if not, I mean, maybe it's not, because balancing equations is a tough thing to learn for a lot of students. Usually one of the key topics that people have problems with. All right, then if not, then we'll keep going. Hopefully this is a good example. So now with these equations, what we can say about them is not just how many molecules of one reactant react with another amount of molecules of another reactant, but we can say that a certain amount of moles react with a certain amount of moles. So these coefficients represent the molar ratios. So I'll write that down. That's a very important concept. Coefficients, I'll try coefs, represent the molar ratios. So in other words, I can say that 3 moles of magnesium hydroxide reacts with 2 moles of sodium phosphate to create 1 mole of magnesium phosphate and 6 moles of sodium hydroxide. That is how you read the equation. That's how I would read it. And you can use these molar ratios to help you with stoichiometric problems like we're going to do now. So in there's many different types of stoichiometric problems, and there's no defined steps. I hate when they write defined steps, but basically, you're going to have a chemical reaction. You're going to balance it. That's always the first thing you do is balance it. So that part's right. I agree with that. So balance it. Then, depending on what you're given, usually it's going to be a mass. You convert it to moles. It might not be of the reactant. It might be of the product. It might be of one of the reactants, not both of them. But you're going to get some kind of mass. You get 15 grams of sodium hydroxide was reacted with 20 grams of blah, blah, blah to create some amount of this. How much was created? It'll be a question like that. And for those, you need to convert some mass to moles using the molar mass of whatever compound you're talking about. And this is where molar mass comes back into play. It will always be a thing in this class. So hopefully you understood when we first learned it and understood it on the test. So then you're going to use your mole ratios that are in the balanced equation to solve for the moles of whatever you're determining. It might be the product, it might be the reactant, it might be something, whatever. It'll be one of those things. And then from that number of moles that you determined, you will go back and calculate grams of your product created, of your reactant used, whatever the question asks for. But the idea is that we're basically balancing the equation, converting to moles, using molar ratios from the equation to figure out the mass of something. That's the way it works. Okay. So, and here's a schematic, whatever. Let's just learn by example. Okay. Sample problem. Wait. Oh, okay. I guess it's already there. All right. So let's take a look at it. Let's drag that out of the way. Okay. So in glucose example, calculate the mass of CO2 produced by burning 100 grams of glucose in excess oxygen. A key thing, when they say excess oxygen, that means there's so much oxygen there that we don't need to worry about how much there is. That's obviously what the word excess means, but it means that there's no moles associated with it. We don't need to calculate the moles or use that in the ratio. We just know that there's more than enough that everything can react fully. So oxygen is not their limiting reactant. The glucose is. And we'll learn about limiting reactant soon. So basically, let's balance this. We did already. Oh, it's already balanced. Sorry. Yeah, so we balanced this before. And you see that you have the 6 coefficients. We have 3 of them right there. So C6, you see that there's 6 carbon. H12, 6 times 2 of the hydrogen. O6 plus 6 times O2. That's 12 plus 6 is 18. And then you see this 18, 6 times 2, and then plus 6 on the right side. So first thing first is balanced equation. Done. Next, let's see how many moles of whatever we're given we have. So 100 grams of glucose. So 100 grams divided by the molar mass of glucose. So let's figure that out. So it's 6 times 12, which is for the carbons. And this is approximate, plus 12, because 12 times 1 for the hydrogens, plus 6 times 16 for oxygen. So the molar mass is, I'm too lazy to do the math. The molar mass is 180. So knowing that, we know that equals 180 grams per mole. So we can divide by 180. And that's going to equal... And that's going to equal 0.5, this number, 0.55. 0.5549 moles. All right. So now, once we know the moles of the reactant in this case, but could be product, could be anything different. Once we know the moles of whatever we're dealing with, let's look at the question. Calculate the mass of CO2 produced by burning 100 grams. Let's look at the molar ratio of glucose to CO2. You see that 1 mole, this is a 1, whenever there's no coefficient, it's a 1. 1 mole of glucose reacts to produce 6 moles of CO2. This means 1 mole, so 1 of C6H12O6 equals 6 CO2. That's the equality that we're dealing with. So if that's the case, then 0.5549 moles of glucose equals 6 times the 0.5549. And that's how many moles of CO2 would be produced in this reaction of 100 grams of glucose. So let's take a look at that math. And they get, you multiply that by 6, you get 3.3. Let's just bring this math up. So you get 3.329 moles of CO2. Now we're going to take that CO2 and we're going to convert it to grams, because the question is calculate the mass of CO2 produced. So we'll multiply that by the molar mass of CO2, which is about 44, and you get 146.5 grams of CO2. Okay, is there any questions on that? So that is a very good comprehensive problem about stoichiometry, and this is just an introduction to it, but if that makes sense, we're good. If not, please ask questions. No? Okay, cool. All right, let's move forward. So now this is one of the most difficult balancing problems yet. It's weird. So there's a way we could actually wait. No, this one's not too bad. This one's one of the difficult ones, but it's not the most difficult. So let's balance it first. Okay, this is a combustion of butane. And butane is C4H10, and then you have the O2, and then you make the CO2 and H2O. Now, this is what can happen this is a good example of what can happen in this chemical reaction. So let's balance it. Let's go element by element, just like we've been doing. And I'm sorry, I feel like I'm a little bit like hazy, like I'm not explaining things correctly, but maybe I didn't get much sleep. Anyway, so C4, right? Carbon 4, carbon 1, put a 4 there. H10, H2, put a 5 there. Now it gets a little bit difficult. So O2, right? Oh, we can put some coefficient there. Let's see how many oxygens we have on the right side. 4 times 2 is 8. And 5 times 1 is 5. So you have 13. O2, that's kind of weird, right? You need some kind of multiple of 2 to go into 13. And we all know that's not possible. But you know what you do? You do it anyway. I'm going to put 6.5 here. Screw it. Whatever. I don't follow the rules. So you put 6.5 there. But professor, you can't have 6.5 of a molecule. You're right. You can't. You could have 6.5 moles, though. But even if you don't want to have that, there's a way to get around it. So that's just disclaimer here. These equations with the decimals in them, they are not standard. You always want whole numbers. But in stoichiometric problems where you're dealing with many moles of something, you're allowed to have 0.5, 0.25, things like that. But for on a molecular basis, we know that 1 mole of C4H10 does not react with, 1 molecule does not react with 6.5 molecules of O2. That's just not possible. So what actually happens is if we multiply this entire equation by 2, as some of you could have guessed already, here's what you get. Nope, that's not what you get. You get 4 times 4, or sorry, you get 2 C4H10s. I got this. C4H10s plus 13. Oh, damn. There's a button on my pen. I still don't know what it's used for. It just messes me up. Plus 13 O2 yields 8 CO2 plus 10 H2O. And if you look from there just to check your work, you see there's 8 carbons, 20 hydrogens, 20 hydrogens. 13 times 2 is 26. 8 times 2 for oxygen, 8 times 2 is 16, plus 10 is 26. So we have this as a balanced equation. Now, but I'm going to stop here. Does that make sense? Is there any questions there? And another thing is you will only encounter this 0.5 dilemma in combustion reactions. And it happens maybe like a third of the time, actually, where you're dealing with bigger organic compounds like butane. And the balanced equation, you're going to end up getting 6.5, 5.5, and you're going to have to multiply the entire equation by 2. So hopefully we feel comfortable doing that. If not, please ask a question. I'm surprised that there's not as many questions as I originally thought, because this is like new stuff. All right. Well, I guarantee you there will be questions when it comes to limiting reactant. So far so good. Good job. If you understand it. If you're just on your phone and not doing on Instagram, I can't blame you because I'd probably be on Instagram too, but try to pay attention. Okay, so let's answer the question on the bottom. Now, using the balanced equation, how many grams of H2O will form from 134 grams of butane, which we have here? So let's look at balanced equation. We got it. We know, let's look at H2O and butane. We know that 2 moles of C4H10, which is butane, 2 moles of it react to produce 10 moles of water. So if we have 134 grams, how many moles and how many grams of water will that make? So let's do it just like we did before. 134 grams divided by the molar mass of butane, which is 4 times 12, 48, plus 10 hydrogens, you get 58. So 134 divided by 58, and using my calculator, let me see. So 134 divided by 58, 2.31. All right, 2.31. That's 2.31 moles of C4H10. Okay. So now let's look at the molar ratio. We know that 2 moles of C4H10 reacts to produce 10 moles of H2O. Now, if that's the case, we got to multiply by the ratio. So in this case, it's a little bit less straightforward than the other one, but we can still use dimensional analysis. So unit conversion, very important skill in this class. So we're trying to convert moles of C4H10 to moles of H2O. Now, if we know that 2 moles of C4H10 reacts to produce 10 moles of H2O, these can cancel out, and we get whatever this is multiplied by 10 over 2 or multiplied by 5. And this, whatever our answer is here, this will be the moles of H2O. But we can go a step further. We can say 1 mole, I'll write mole this time, 1 mole of H2O is equal to 18 grams of H2O. So we can cancel out moles and moles, and from here, in one full step, we can go from the moles of C4H10 to the grams of H2O. So if we do this out, we get 2.31 times 5, or times 10 over 2, same thing, times 18. And that's going to give us 207.9. So it'll be 207.9. That's going to be grams of H2O. Okay. Any questions? No? Yes? You guys are still there, right? Someone can just, okay. Does this work? Okay, thank you, Olivia. Thank you for making sure I'm sane, because like nobody said anything, so I'm like, did my internet go out again? Does this work backwards too? Yes. So if you had a question of, oh, you do some kind of reaction and you get 5 moles of water, how many moles of O2 was reacted? Perfect. You could do the same thing, if that's what you meant by backwards. Okay, cool. So yeah, you could do it either way. That's what I love about stoichiometry. Using these molar ratios, you can solve literally any question involving the reaction. So, all right, let's do a crazy hard balancing problem. All right, so this one is nuts. Basically, so what I'm going to do is I'm going to make a new slide. I'm going to put, I didn't even learn these in college growing up. Like the first time honestly, the first time I've ever seen these crazy ones was when I started teaching here. because it's just not in any book. But, and also, disclaimer, they're not going to be on the test because it's insane. Wait, actually it might. If there is, I'll take it off because it's pretty difficult. But basically, let's try to solve this using our old method. So, you have copper. One copper there, one copper here. You have hydrogen. 2 hydrogens here, 1 hydrogen here. You put a 2. Nitrogen. 2 nitrogens, 2 nitrogens. Oh, wait, 3 nitrogens. What do I do? You kind of encounter a crossroad. Like, should I put more here? Should I put a coefficient here or here? What do I do? Then oxygen. 2 times 3 is 6. There's 6 of them here. 7, 8. And there's 3 sources of oxygen. That's insane. So we can do the following. So let's do this. We can put variables. Let's put A. Let's put B. Let's put C, D, and E. These variables, we can make associations with them. And we can basically, if you're good at math, well, most of you should be good at math because you're at the school. We're going to be solving a system of 5 variables, 5 equations, 5 unknowns. Okay, nobody left, so that's good. That means you're ready for this. I wasn't ready for this, honestly, but let's try to get some associations from it and figure out how you do it. Now, copper. Copper is just lonely by itself. And the number of coppers on the right side is also 1 initially. So this means that whatever A is, whatever the coefficient of this copper is, the coefficient of this copper nitrate, has to be the same. Because you can't have 1 here and 2 here, or else it's not balanced. The coppers need to be balanced. So you know that A has to equal C. Now let's look at B. So B, let's look at just hydrogen. So hydrogen, there's 1 of them here, and there's 2 of them here. This means that whatever this number is has to be double E, right? Or else hydrogen won't be balanced. So B has to equal 2E. See, this is complicated. So B has to equal 2 times E. So let's check that work. So if you put in 1 here, if you put in 1 for E, B has to equal 2 times it. B has to equal 2, and that makes sense because it would be 2 hydrogens here, 2 of them here if you had 1 over there for E. Okay, good. Next, let's look at C, or let's look at B for nitrogen. So you have B for nitrogen. So you have 1 nitrogen here. You have 2 of them here, 1 of them here. So this means that B has to equal 2 times C, 2 times C plus whatever D is. So because D is only, you need this nitrogen plus these nitrogens to equal these nitrogens. Does that make sense? Hopefully it does. Next association is, and once you get these equations, by the way, it's just a matter of grinding it out. So let's look at C. Let's look at oxygen. Sorry, let's look at B for oxygen. So that's the last element we have left. So B for oxygen, we have 3 oxygens. So let's put 3B. On the right side, we have, associated with C, we have 6 oxygens. So has to equal 6C plus D, we have 1 oxygen, so plus D. And then E, we have 1 oxygen plus E. So there are 4 equations. I don't think we can get 5. So I think it's 4 equations, 5 unknowns. Because A equals C. So it's basically the same as, this is already 1 equation done. Okay. So let's try to figure out stuff from this. All right. So take some time to look at it. But there's different ways to approach it also. So if we do, we can replace, you see B, we have two equalities for B. You can make 2E equal 2C plus D from these two equations. You can totally do that. And then since we know that A equals C, you can put in A there. That doesn't really help us. Okay, so let's see what else we got. You can use this equation, and you can put 2E in there. So let's do that. We could do 3 times 2E equals 6C plus D plus E. Or you can solve for C there. You can do a lot of different things. I'm going to go back to the work and see what they do first. We have a structure, but it's just to show you different paths you can go. You can solve for C in this equation. So if we do that, we get B minus D over 2 equals C, which also equals A. So you can do that. But let's just cut to the chase. I don't want to spend all day on this. All right, so here's what they do. So they first took B equals 2E, and they used the B equals 2C plus D equation and replaced B there. So I think we had that right here. So they did this, and they figured out D from there. And then they took that D and put it into the oxygen equation right here to make this. And then they reduced it to E over C equals 4 over 3. So they have E equals 4, C equals 3. If that's the case, you know, because A equals C, that A is also 3. So now from that one step, you have 3 equations, or you have 3 of the variables solved for. Then you can use B equals 2E, and you can solve for B, and then you can use D equals 2E minus 2C, put in 4 for E and 3 for C, and get your final variable. So yeah, this is really tough, but you basically have to work with it. But it won't be on the test. I'm not going to be that mean. But yeah, does that kind of make sense of how, like, I just want you to be aware that this exists. And if you were, like, gun to your head, you would have some idea of what to do. And if someone told you, solve this chemical balancing equation or I'll kill you, you would have some idea what to do. If the traditional method doesn't work, you would know that this method exists. So take that as you will. Is there any questions on it? I know there might be. I'm probably going to make a video on it alone because also this works for everything. One of my students in the winter course, they're really good at computer programming and stuff. And they did this method like spoke to them. So they started solving all their balancing equations with this. It does take a little bit longer, but it works for every single one. And the ones that are easier, obviously you can imagine, there's not 5 variables with all these weird associations. It's very easy. A equals 2B, B equals 2C. It's similar. It's very simple like that. But this works for all of them. Okay, so let's do this one. You see the answers, but whatever. So let's do this one. I'm going to take it and put it here. All right. So this one is fair game for an exam. So let's just go through it. C6, 6 of them. CO2, put a 6 there. H14, put a 7 here. 7 times 2, 14. O2. All right, let's see how many oxygens there are on the right. There is 6 times 2, which is 12, plus 7 times 1, which is 7, is 19. So now we have O2 and we have 19. So what is the multiple of O2 that goes into 19? It's going to be 8.5. Or no, 9.5. 9.5. Okay. So we have 9.5 O2, and then we can multiply the entire equation by 2 like we did before. And we get 2C6H14 plus 19 O2 yields 12 CO2 plus 14 H2O. And you can see how this works out. There would be 38 oxygens total. There's 24 plus 14, which is 38, and there's 38 here. Okay, so hopefully that makes sense. Here are some more to practice on your own, and I'll actually give you right now a couple minutes to do that on your own. So right now it's 9:52. I'll give you until 9:55, and you can work on these on your own, just to give myself a break from talking. Or to ask questions, if you want. You guys seem quiet today. I hope everything's okay.
I woke up like 30 minutes ago.
Yeah, me too.
I woke up 5 minutes late for class already.
Yeah, that's what happens. Nobody wants to do a summer class Monday, Wednesday, 9 a.m. for 3 hours. I understand that. I mean, I wouldn't be doing it if I didn't get paid. So, well, I do like it. That's a lie. I do like it, but I would have picked different times. I wouldn't want to do 3 hours. It is what it is. As long as you understand balancing. The two main things from this chapter I want you to get are balancing and limiting reactant, which we didn't cover yet. But it's basically just advanced stoichiometry. But you should, like, if you understood the stoichiometry we did so far, then limiting reactant will be not too bad. Yesterday was my birthday, so happy birthday to me.
Happy belated.
Thank you.
Belated. I thought it was the first or the day of. No? It's
No, the
not.
second.
That's tough.
Thank you. Thanks, everybody. I don't think I've ever heard the word belated except for talking about birthdays. Did you do anything cool? No, I went to my lab. Actually, no, I did what I wanted to do. I woke up late, and I was like, today, even though you really can't do anything, you really can't hang out with friends or do anything because of the virus, can't go out to drink. I was like, I'm going to do something I want to do. So I woke up at 11, and then since I got my gym set up in my garage, I was like, I want to bench right now. So I just, for like 2 hours, I want to bench, so I benched. And then I went to my lab, and I did an experiment, and then I left. And then I got ice cream. So screw it, whatever. That's my fun. And then I prepared for this. Yeah, pretty solid day. I know. It was good. And I was supposed to watch a movie. I was going to watch a movie, but I didn't. Okay, so.
Can you give us a hint on how to, because, like, I know these are hard, but if you know which one to start with, it becomes easier. How do you determine which one you want to start with?
Right. So I always start from the left side, and you start from the first one. That works every time. Sometimes you do have to change variables, and you have to go through it twice or even 3 times, but it will work if you do it right. So let's do the first one. The first one is more difficult than the second, but the second, there's a rule in there. There's something that there's a little nuance that I want to teach once we get there. So I'll start to go over them now. All right. So HiO3, this is iodide. I think it's iodide, yeah. But anyway, so let's go through it. You have hydrogen. There is 2 hydrogens here. Now, is a rule. If there's 2 of one element on one side, you ignore it for the time being. Wait a minute, there's 2 of all of them, except for iron. But we'll see. We'll deduce as much as we can. This is a tough one. So let's leave that alone. Actually, we don't have to because look, there's 2 hydrogens here and there's 2 hydrogens on the right side. So I think we're pretty good with that. Next is iodine. There's 3 here. 1, 2, 3. And then there's 1 here. So most likely you might have to put a 3 there. Let's do that now. And really see what happens. Iron. There's 1 here and there's 1 here. Leave that alone. Iodine. We just did that. There's 3 here. 3 here. We're good. Hydrogen. We just did that before. 2 here. 2 here. We're good. Chlorine. There's 1 chlorine here. There is 3. Bless you. There is 3 and 3. Bless you again. There are 6 chlorines on the right side and only 1 here. So we have to put a 6 there. Now, hydrogen's different. So we have hydrogen 1, 7. To make this work, if we put in, let's see, so we have 7 hydrogens, and this is going to be, if we put a, let's put a 2 here. So it gets difficult, so you have to kind of like guess. Not guess, but like educate. If we put a 2 there, and we put, it would be 2 times 3 is 6, and then you'd have, that's for the oxygen. Here you would have a 6 there. Oh, wait a minute. Did we forget to balance oxygen? That's why it says weird. We forgot to balance oxygen. All right, let's start over. I'm sorry. All right, let's start over. It's a different color. All right. So hydrogen, 1, 2, 2. Leave it alone. Iodine, 1, 2, 3. Put a 3 there. Oxygen, 3. Oxygen, 1. Put a 3. Hydrogen's different now. So let's leave it alone for now. Let's just leave it alone. And then we'll go to iron. Iron, 1, 1. Good. Chlorine, 3, 1. Put a 3. Now let's take a look at hydrogen. 1, 3, that's 4. Hydrogen, 6. Okay. So if we put a, how the hell do you solve this? This is a tough one. This is a really tough one. So if you put a, wait, if you put a 6 here, hold on, this isn't, the chlorines aren't balanced because there's 3 chlorines here, 6, that makes 6 of them, so we have to put a 6 there instead of a 3. So let's do this. So this part was wrong. Put a 6 there. So if we have that, then we have 6 chlorine, 6 chlorine. Now hydrogen, you have 7 and 6. If you put the, I don't even think you can solve this traditionally. Yeah. Yeah, that's what we're getting to. We have to use the method, the coefficient method. All right, let's do that. All right, we got this. I'm sorry. We got this. So let's do this. A, B, C, D, E, F. Why would I give this to practice on your own? Wow, that's pretty mean of me. So let's do this. So we have hydrogen. So we have A for hydrogen. A plus C has to equal 2F. For iodine, A plus 2B. See how, or sorry, no. Yep, A plus 2B because this is iodine here. A plus 2B has to equal E. That should be an equal sign. So yeah, this works 100% of the time. And then for oxygen, we have 3A has to equal F. And then we have, that's it, Cl. Cl, we have C has to equal 3D. Yeah. No, 3D plus E. Okay. I think that's everything.
Iron.
Okay.
Oh, iron. Duh. Okay. Iron. So iron, we have, oh, what did I just do? What did I do? No. Okay. So iron, we have B has to equal D. Cool. All right. Solvable. All right. So if we take immediately the thing that jumps out to me is A plus C equals 2F, and we know that F equals 3A. So if we replace that, A plus C equals, it would be 6A, right? So 2F, and then F equals 3A. 3 times 2 is 6, 6A. And then we could figure out what C is. So we subtract, we have C equals 5A. Okay. Then we have this equality, and then, so then we can figure out, we have that. So then what we can do next is B equals D, not yet. We can use, really there's many ways to approach this. You can do A, this one. We could use this one. Let's use this one. And let's use the iodine and the chlorine. Actually, no. We can use the first one again. So if you know that C is 3D plus E, you can do A plus, replace this C with 3D plus E. That equals 2F. And then we know that B equals D, that wouldn't help us. We can solve for F. We can put in F again equals 3A. Damn, this is complicated. So we can put in F. Oh, no. We can put in that F equals 3A. So we can put in A plus 3D plus E equals 6A. And then we can subtract the A's. Again, we get 3D plus E equals 5A. So then we also have 3D plus E equals C, because we know that 5A equals C. So we have that equation also. And then we know that B equals D. So we can also know that. And then for E, we got to use this equation too. So we know that E, we can go from here, we go 3D plus, replace E with A plus 2B equals E. And now since we know that D equals B, we can do 3B plus A plus 2B, which is 5B, equals E. So we have 5B plus A equals E. So we have this equation. And then we need numbers now. So we have everything we need. Oh, these are the same equation almost. These are the same equation. So let's figure out numbers. Let's use this. So we can do divide by A. You have C over A equals 5 over 1. And let's go from there. So we know that C equals 5, A equals 1. Okay. So then let's look at this one. Or let's look at this one. You have A is 1, so 5B plus 1 equals E. You have, where can we go from here? You have, oh, we can find F. We can find F. So we know that A plus C is F. A plus C is 2F. So 6 equals 2F. 6 divided by 2 is 3. F equals 3. Okay. So now we have C, A, and F. So we go back here. We can do we know that C is 5. And we could use this chlorine equation. And we can do 5 equals 3D plus E. And we know, what do we know about E? So we know that, here we know that E is 5B plus A. That's not true. E is, hold on, cross that out. We're using this equation right here. So A plus 2B equals E. So we have A is 1 plus 2B equals E. And we know, okay, we're getting somewhere. So we know that E is, so in this equation, we know that E is 5 minus 3D equals E. If we just move this over there, and now we can get rid of this E. If you lost me, it's okay. This is a shit show. So minus 5, 3D. We replace that E with this E. And then we have B and D. They're equal to each other. So that doesn't really help us. Great. We're almost there. Almost there. It's even for me, like this is I didn't do this. I never did this one before. So it takes trial and error. So we have 3 of them. Anybody come up with anything else that I don't see?
Yeah, I have an idea.
Okay. So we have these 3. What's next?
Oh, from here, I had a different plan.
Oh.
Well, we have C is 5, A is 1, right?
Right.
And then we can take the CL equation, solve it for E, and then substitute it into the I equation.
And then put it into the I equation. Okay, so you have, let's do that. Let's erase some stuff first. Let's erase this. All right, so we can put that into the I equation, and we'll get A plus 2B equals C minus 3D.
And then, you know, A is 5, A is 1, C is 5, and you know B is equal to D, so you can solve that.
Yes. Good. So 2B equals C is 5 minus 3D. So then, that's what I had down here.
Oh.
Yeah. So yeah, good. So then we could subtract and we get 2B equals 4 minus 3D. That really wouldn't, that would just give you.
We know B is D. So
we know B is D.
5D's or 5B is equal to 4, and then you'd get a fraction.
Yeah, so we need wait, hold on. So 2B plus 3D equals 4. And then we know they're equal. So it would be 5B equals 4. And then we have B equals 4 over 5.
And then that's equal to D, and then you have...
Right. Okay, good. So that's awesome. Nice job. So B equals 4 over 5. D equals 4 over 5. And then we're done. A, we have B, we have C, we have D, we don't have E, but we can figure out E. We know E equals C. Do we? No, that's half an equation. So we have A and B. So we have A is 1 plus 2B is going to be 2, so 8 over 5 equals E. So that's going to be 5 over 5. That's going to be 13 over 5.
And then you can just multiply everything.
Multiply everything by 5, right. So, okay, good job. All right. So that was a shit show. We got it, though, thanks to you guys. Let's see if it works. So A is going to be, then when you multiply everything by 5. So A times 5 is going to be 5. So A equals 5. B is 4 over 5 times 5 is 4. C is going to be 5 times 5 is 25. D times 5 is going to be same as B, which is 4. E is 13 over 5. And that's going to be times 4 times 5 is going to be 13. And F is going to be 3 times 5 is 15. All right. Let's see if that works out. Oh, I should have been more prepared on that one. Usually I give this example. You know what that means? That means no one does it. Because I gave this example for the last 2 years or the last 2 semesters, and no one has questioned, like, Professor, can you go over this one? They're just like, all right. I'm like, do you guys get this one? When I show the answer, and they're like, yeah. That means no one did it. So thanks. Thanks for
Same thing happened in my physics class earlier this semester.
yeah, like he put in yeah.
It was the lab journal though. It was an entire lab.
Oh no.
I was trying to finish the lab and I was like, Professor, this equation makes no sense. Leaves the room for 20 minutes, comes back. He's like, yeah, the lab journal's got to get rewritten.
Wow. Yeah. I'm still learning, but we got this. All right, let's see if this works. So hydrogens, let's add them up. 5 plus 25 is 30. 15 times 2 is 30. Yay. Iodine, 5 and 8 is 13. 13. Nice. 5 times O3 is 15. 15 times O is 15. Iron, 4 and 4. Chlorine, 25. And then you have 13 plus 12 is 25. Hey, we got it. Yay. Okay. Whew. All right. Thank you. Now I know for the future that I'm not going to go over that one. I'm just going to not include it.
And you said the second equation was harder, right?
No, the second one is just a little nuance. This one, no, this one's not too bad. But there's something that you have to know about it. So I use a different color. I use blue. All right. So this is an acid-base neutralization equation. So acids and bases, this is hydrochloric acid and barium hydroxide. When they react together, you get water and a salt. In this case, the salt is barium chloride. Now, when you balance this, I'm going to balance it like you normally would, and I'm going to show you what happens. So if you do that, you have hydrogen is 1. Hydrogen, there's 2. So you put a 2 there. Chlorine, there's 2. Chlorine, you put a 2 here. Ba, there's 1. You put a 2 here. Hydroxide, oh, where's the hydroxide? I'm confused now. So you kind of encounter an error. Or even if you want to do all the hydrogens at once, you still would get an error. So here's what you do. First, whenever you see an acid and a base acid and a base neutralization, and the way you notice it is one, you see a hydrogen in the front. Like we learned about acids and bases and what they look like at least. And you see an acid in the front, a hydrogen in the front. And for a base, you see usually a hydroxide in the back. On the right side, you're going to see water written as H2O and barium and some salt. If you rewrite water as HOH, you're good. That solves all the problems. Because the hydroxide is conserved from the left to the right side in that case. So someone has their mic. I'm going to mute everyone. Okay. So if you do that, that solves the problem. So let's go through it now. H and H. We're comparing the H's to the H's and the OH's to the OH's. So H to H, we have 1 to 1. We're good right now. Cl to Cl, we're good right now. Barium to barium, we're good right now. OH, there's 2 OH's, 1 OH here. Put a 2 there. Then that makes there's 2 hydrogens, 1 hydrogen, 2. Putting the 2 here makes 2 chlorines, 2 chlorines, 2. Wait. Hold on. Am I losing my mind? I'm rewriting this. I'm losing my mind. So we have HCl plus BaOH2 yields HOH plus BaCl. 2. That's what's wrong with it. BaCl2. Typo. Okay. Let's do it again. Wow, this slide sucks. Oh my God. I'm getting rid of it. Or I'm going to just fix it. So let's go through it again. H, we're good. Cl, we're not good. Put a 2 there. Now we have to put a 2 here because we changed the hydrogens. Barium, we're good. OH2, we're good. Done. Whew. All right. Any questions? Yeah, Gus, it was a loop because this was wrong. BaCl is not a thing. It's barium. So barium is in group 2A. So it's 2+, meaning chlorine is 1-, and it has to be 2 of them. So there was a typo. And no one in my 2 other sections questioned either of these questions. And they're both, and one of them is wrong, which was this one, and the other one is really difficult. So, yeah. 2 years of children suffering. Yeah, well, or they just didn't do it. That's what I think. They just ignored it. Because they didn't want to seem stupid, even though they weren't. But they thought everyone else got it because no one else asked any questions. So, okay. Let's do limiting reactant. How about that? Is there any questions on balancing? If you get these, you get every one of them. So, yeah. All right, let's do some limiting reactant. I'm really sorry about this. You know what I'm gonna do? I'm gonna make a YouTube video later about balancing equations. It's gonna be really concise and good. I feel really bad about this, so I'm gonna do that later. Okay. Now we're gonna learn about limiting reactant. So what the limiting reactant is, we know about this. What the limiting reactant is in some equation. Let's say this equation. If you're doing a lab and there is certain amount of each reactant that's added together, one of them might react completely. The other one will be in excess. So if you have all the oxygen gas in the world, right? If you have an excess of oxygen gas like we saw before, and you are burning wood, let's say, right? You have a limited amount of wood. You have an excess of oxygen. The thing that limits the progression of your reaction to the products is going to be the amount of wood you have. The more wood you have, the more combustion products you can make. The more CO2, the more heat, the more H2O that you can make. So it's our job in certain chemical reactions, knowing the initial amounts of reactants, to figure out which one is limiting the reaction progression, meaning which one runs out first. So that's the definition of it. And here's a good example of that, where you're reacting methane and water to create hydrogen gas and carbon monoxide. And you see that 1 molecule of CH4 reacts with 1 molecule of water to create 3 molecules of H2 and 1 molecule of CO. And you see that here you have pairs of 1 and 1. This will react, all the pairs will react. But there is an excess of H2O. That means that methane, the CH4, is the limiting reactant, because the limiting reactant reacts completely. It reacts and it dictates the extent of the reaction. So it's our job to figure that out based on what we know already about molar ratios, molar masses, and all that stuff. And basically the way it's going to work is the limiting reactant is the one with the least amount of moles in the using the molar ratio. The least amount of moles reacted using the molar ratios. Usually it's the one with the least amount of moles in general, but not all the time. So there's this thing. I hate these charts about how to. I feel like nobody reads these. I didn't growing up, but basically what we're going to do is balance the equation first. Always balance the equation first. Then we're going to convert our masses to moles. We're going to determine how much product is produced from our reactant moles. And then we're going to determine which one of those reactants creates the lowest amount of product. That one happens to be the limiting reactant. So let's do this. So let's do a new slide. We'll do this together. So we have equation. Pretend there's an arrow there. We have an equation, and then we have this. So our questions would be generally like this. You have a vessel with 300 grams of water, 250 grams of methane. What is the limiting reagent? How much CO is produced? Okay. So let's balance it first. You have CH4 Oh, it's already balanced. Let's double check. So there's 4 of them, 6 of them here. Carbon 1, oxygen 1, oxygen 1. Good. All right, balancing is done. Next, 300 grams of water. So let's immediately find the moles. 300 grams of water divided by the molar mass of water, which is 18. 300 divided by 18. Let's see. 300 divided by 18 is 16.67. So 16.67 moles of H2O. So that's one reactant. Second reactant, 250 grams of CH4. Molar mass of CH4, 12 plus 4 is 16. And this is going to be 250 divided by 16. 15.625. 15.625 moles of CH4. Okay, so now let's see how many moles. Okay, so this is where people get confused. To figure out the limiting reactant, once you have the moles of each reactant that's reacted, you can pick either product. You can pick any product. Let's pick CO just to get to the question, just to do the answer, and then we will pick H2 and see what happens. So we can compare, or we can determine the amount of product of either product that is created from the reactant moles individually. Whichever one creates less of the product is the limiting reactant. So going to CO, 16.67 moles of H2O. If you look at here, H2O, there's one of them to 1 CO. The ratio is 1 to 1. That means if you have 16.67 moles of H2O, it will create 16.67 moles of CO. Same thing for methane. Methane is a 1 to 1 ratio with carbon monoxide. If that's the case, you'll have 15.625 moles of CO created from the methane. Now, which one is limiting? Which one limits the progression of the reaction? Someone tell me in the chat or by saying it. Good, CH4. Good job, Gus. And the reason why is because there is less moles of it to react, and it produces, well, that's not why. The reason why is it produces the least amount of moles of our product. So if you react both of these together, there will actually be an excess of H2O, and that excess you could even calculate as the difference between this. So the difference of these moles will be the excess because it's a 1 to 1. So you'll end up with whatever 15.625 is times the molar mass of carbon monoxide, which is 16 plus 12, or 28. So multiply it by 28, and you get 437.5 grams. Okay, does that make sense? This is a relatively easy example, but we'll do another one.
Could you just repeat the 28 again? Where did?
Yeah, 28 is the molar mass of carbon monoxide, and the question is asking for how much CO is produced. So once we know that methane is the limiting reactant, we take that amount of CO, the product, that is produced from the limiting reactant, multiply it by its molar mass to obtain the amount produced. Okay, so now let's look at the other product. Let's look at H2. So we know that we have this many moles of, well, let's erase this part. So let's look at, this works for either product. So let's look at H2O. All right, or sorry, H2. If we know that 1 mole of water makes 3 moles of H2, 16.67 will make whatever that is times 3 of H2. So 16.67 times 3 is 50. So 50 moles of H2. For methane, same thing. 1 methane makes 3 H2. 15.625 makes 3 times that, maybe 47 or something. Yeah, so 46.87. So you can see here that even if you compare the other product, you still get methane as your limiting reactant in this case, the one with the lowest amount of produced moles from that starting point. So yeah, so you can figure out anything from limiting reactant. And you can even figure out how much is in excess. So if we did that, we could see that, all right, 1 mole of reactant 1 reacts with 1 mole of reactant 2. So if we have these mole numbers, we can subtract them and get 1 point whatever moles. Let's do that right now. 16.67 minus 15.625. You have 0.0425 moles times H2O molar mass, which is 18. And so I'll write that down. Wait, where's the history? There we go. Okay, so to figure out the excess, we can do 16.67 moles of H2O minus 15.625 moles, because 15.625 moles of the H2O will react because it reacts in a 1-to-1 ratio with methane. So the remainder is going to be simply the remainder is 0. Wait, that's not right. Oh, I messed up my math on my calculator. Well, everything I wrote down was correct, but I messed up on my own. I put 16 point instead of 15 point. And you get 1.045. That's how many moles. And then you can multiply that by 18, and you get around 1.045 times 18. You get 18.81. So you can even figure out how much was remaining in excess. Okay, so let's do another, or so before we do another limiting reactant, let's go over another thing you can figure out. So there's a thing called theoretical yield. So theoretical yield is the on paper amount of product that can be produced from a given amount of reactant. Everything that we just determined with this limiting reactant problem is theoretical, because we don't know that in a chemical reaction, in this reaction, we calculated that there will be how many grams was it? 437 grams of carbon monoxide. We calculated that as this reaction will produce that much. If you do this reaction in a lab, I guarantee you will not get that much. You'll probably get 400 grams. That's considered really good. That's a 90-something% yield, or 80-something%. The idea is that in a real world setting in a lab, you're not going to get 100% yield virtually at all. So they have this thing called actual yield, meaning it's the amount of product that is produced from the chemical reaction in the lab when you actually do the experiment, which is all the time going to be less than the theoretical yield. And then from that, you can get the percent yield, meaning how much percent of the theoretical value did you actually get. The higher, the better. So we can do a comprehensive problem. So here's how it works. We'll do a big comprehensive problem from the homework. But so in this methane example, if the actual yield was 337, what was the percent yield? So we figured out that the theoretical yield was 437. So you do 337 divided by 437 times 100, 77.1%, which for some reactions is pretty good. So, and also to give you an idea, like for every reaction, 100% yield or 90% yield sometimes is not attainable. Sometimes you have some of the reactants go in the environment. Sometimes there's different gases that are produced. For example, in some organic synthesis that I'm involved in, some of the reaction steps only have 30% yield, 20% yield, and that's the best. Even in like the best scientists in the world, in the literature, that is the best they can get because of maybe it's very endothermic and it creates other heat and it creates other things going on, and you just lose some mass. It happens. So that is that. So let's do this problem. This is from the homework, so you better thank me. So I'm going to move it to the top up here. Okay, so we have a big reaction here, and we can write everything out. So hopefully this will encompass everything, and we'll do it correctly, or I'll do it right. So the reaction of 9.32 grams of Cl2 with 2.2 grams of P4 produces 3.64 grams of PCl5. All right, so before we even talk about the masses, we're going to write the equation. Cl2 plus P4 equals PCl5. All right, so now the first step always is to balance the reaction. So let's balance the equation. Cl2, Cl5. Let's put a 2 there and a 5 here. That's the least common multiple. For P4, we have 2 times 5. 2 times 5 is 10. P4, all right, sorry, I'm looking at chlorine. 2 times phosphorus is 2. P4. So if we just multiplied these two by 2, so if we did, this was a 4, this was a 10, and then we left this as 1, it works out. So let's double check. 10 times 2 is 20. 4 times 5 is 20. For phosphorus, you have 1 times 4 is 4. 4 times 1 is 4. So any questions on that balancing? That was just kind of just like it's not too hard. You just deduce it, and you go through the process, and you'll get it. Okay, next. We have to figure out the moles of what's reacted. Let's just quantify all this. So we have 9.32 grams of Cl2. Not Cl, Cl2. So let's figure out the molar mass. Cl2, we know that each mole, or just Cl, 35.45. If you look at the periodic table, multiply it by 2, and you get 70.9. So 70.9 grams per mole. And by the way, on your homework, the numbers are different, so you can't just copy this answer. But we'll go through how to do it. So let's figure out the moles. 9.32 divided by 70.9, and you get 0.131 moles of Cl2. Now let's look at phosphorus. So phosphorus is P4. So we have, according to the equation, 2.20 grams of P4. Phosphorus, the molar mass is 30.974. 30.974 times 4, because the P4 is a molecule. So you have 123.89. So 123.9. 123.9 grams per mole. We can divide that out, and we do 2.2 divided by 123.9, and we end up with 0.0178 moles of P4. So now we have that. Is there any questions up to this point? So we figured out the amount of moles that we have of our reactants. So now our job is to figure out how many moles of product does each one of those reactants correspond to if it reacts completely. So we're only taking into account one reactant at a time. So let's use a different color. And let's just do chlorine first. So let's look at chlorine. 10 moles of chlorine gas, make 4 moles of PCl5. So if that's the case, we can do our dimensional analysis, and we know that 10 moles of chlorine corresponds to 4 moles of PCl5. Moles of chlorine cancel out. I'm using Christmas colors. That's cool. I didn't even notice that. So 4 moles, or so the moles of Cl2 cancel out, and you end up with whatever that is times, let's see, 0.131 times 4 divided by 10. And you end up with 0.0524 moles of PCl5. So that's how much is produced. That's how much is produced if the chlorine gas was reacted to completion theoretically. So hopefully that terminology makes sense. It's based on the chlorine only, and it's theoretical. Okay, next. Let's do the same thing for phosphorus. So we know that 1 mole of phosphorus reacts to produce 5 moles of PCl5. So let's do that same reaction here. 1 mole of P4, because we want that to cancel out, reacts to produce 4 moles of PCl5. Multiply that by 4, and what do you get? 0.0178 times 4, and you end up with 0.0712 moles of PCl5 produced. All right. Now, looking at these, there's 2 things I want to mention, or there's 1 thing I want to mention. The thing is, you notice how phosphorus started out with the lowest amount of moles by a lot. The chlorine gas had almost 10 times the amount of moles that P4 had. So you would think, oh, P4 is limiting reactant. Well, once you do the stoichiometric ratios and you take them into account, you see that the opposite's true. So that gets to my question is, which one is the limiting reactant? I want someone to write it in the chat or say, just to know that you guys are still there.
Chlorine, right?
Yeah, chlorine. Good. So chlorine is a limiting reactant because when it reacts fully, it only reacts to produce 0.05 moles of PCl5, whereas P4 reacts to produce 0.07. So now our question is what's the percent yield? To get there, we have to figure out how much is theoretically reacted, because these are all theoretical values. The actual value is given. Most of the time it's going to be given because you're not going to be carrying out this experiment. So that's why we didn't use this number yet. We didn't use PCl5. We didn't use the grams of it, because that is an actual yield. So theoretically, let's do that here. 0.0524 times the molar mass of PCl5, which is 30.947 plus 5 times 35.45, 208. So you take that number times 208.2, and you get, let's see, you get 10.91. So yeah, that's a decent amount. So you get 10.91 grams is the theoretical yield. I'll put theor yield. Okay, so does that make sense?
Yeah, the 208 is the molar mass of PCl5, right?
Correct, yes.
Okay.
So I'll put an arrow to that. Put molar mass. Okay, so now we can figure out the percent yield. Percent yield is the actual, which is 3.64, divided by the theoretical, which is based on our limiting reactant. So that's why we need to find limiting reactant first when we do these problems. So from now on, I want you guys to think whenever you're solving any stoichiometric problem where they give you the amount of reactants, always think which one's limiting, which one's limiting, which one's limiting. Because if you don't, you'll be either guessing or using both or doing something different. But you always need to be thinking in those terms. So times 100, it's about 30% or probably 30%. I don't know. Let's see. 10.91, 33%. 33.4%. So that is the percent yield. So now, other questions that can be asked is how much is in excess? So that was an easy example before, the first example, because it was a 1-to-1 ratio. This time, we're not having a 1-to-1 ratio. It's a bit different. Now, to figure out, the question would be maybe this for part A, and then part B would be how much of the P4, which is not the limiting reactant, how much is left over? So here's the way you would do it. The stoichiometry is cool that you can kind of go backwards and forwards like this. You can subtract these two, right? If you subtract those two, you'll get, let's just for all intents and purposes, 0.02, right? If you subtract the excess from the limiting, that means there's going to be 0.02 moles of PCl5 that is not going to be produced, and it's not accounted for, and it is the amount of reactant responsible for that is going to be whatever reactant is whatever of some amount of P4. So we can go backwards using the ratio and say, all right, if 4 moles of PCl5 makes 1 mole of P4, then this many moles of PCl5 makes or is produced by X many moles. So we can actually go backwards. I'm gonna erase something. I'll erase this. All right, so we can go backwards and we can write 0.02 moles of PCl5 that is produced by, or so that's how much is produced in X, that's how much is not accounted for. And then we can say that for every 4 moles of PCl5 produced, 1 mole of P4 is responsible for it. So 4 moles of PCl5, 1 mole of P4. So the moles of PCl5 cancel out, and you get 0.02 divided by 4. And you get 0.005. 0.005. And this is how many moles of P4 that in excess. And then you can multiply that by the molar mass to figure out the amount in grams. Okay, does that make sense? So you can figure out a plethora of information from just this one sentence.
What about the percent yield?
Oh, it was 33. I erased it before. It was 33.
Oh,
yeah. So so here's how we got the theoretical yield right up here, and then the actual yield's given. So 3.64 grams divided by 10.91, 33.6% yield.
Okay.
Okay. Cool. All right. Any other questions on this? This is a very comprehensive problem. Oh, Daniela message. Where did I get the point? Okay. So in that, so this is a scenario that I was like, oh, what if they ask for this? And that this is the, what if they ask for the amount of excess? Now, if you subtract the moles of PCl5 produced from the limiting reactant and the non-limiting reactant, you'll get this 0.07 and it's 0.05. You get around 0.02. So that is the amount of moles that is not going to be accounted for in the reaction, and the amount of product that's going to be, in essence, lost because one of the reactants was used up all the way. Using that missing amount, going backwards, you can figure out how much of the excess reactant is left over that would produce that missing amount. So hopefully that makes sense. Okay, is there anything else? If not, no. So we're almost done. We got to learn about oxidation reduction. That's pretty easy. So think about this. Who cares? Balancing equations, more of them. Whatever. We're not doing 15-minute break. That's for my other class. We're almost done. So, okay. You can balance these on your own, but I'm going to make a video of balancing equations that it'll be better than what we just did. So anyway, there are these other types of equations called oxidation reduction. And maybe you've heard of this term or redox before. And in essence, well, the equations we've been dealing with so far, if we had ionic bonds, the charges on the left and right side of the equation have been staying the same. For example, or there hasn't been charges at all. Like, I don't know, any of these, right? Or like copper, I don't know. Well, there was some ionic ones before, but whatever. I think some of those were redox. But the idea is that if you do a simple reaction, let's say a double replacement, like I was talking about, I mentioned that before, where there's ions and the ions stay the same charge in the left and right side of the equation. Sometimes they don't. So it involves a transfer of electrons from either one thing in the reactants to one thing in the products, but atom to atom, element to element, there's a transfer of electrons going on. And examples, which we went over already, we're familiar with the different types. There's combustion reactions, there's oxidation, meaning literally it's an oxidation reduction. Of course, oxidation, such as rusting, tarnishing, those are forms of this redox reaction. And there are different things we should keep in mind about redox reactions, and we can characterize them, is what we're trying to do. So here's an example of one where you have sodium and then chlorine, sodium solid and then chlorine gas, and they go together to make sodium chloride. So that's a redox reaction because the electrons are actually being transferred from the chlorine to, or from the sodium to the chlorine, making both of them charged and giving them that sodium chloride ionic structure like we talked about. So there's these, well, before we get to that, let's look at the equation. There's these things called oxidation states, which are basically, I like to refer to it as a pseudo charge. It's kind of like a charge, but not really, where based on its oxidation state or oxidation number of each atom, each atom really. So each atom could have its oxidation number. Based on the oxidation number and how it changes from the left side of the equation to the right side, you can tell if something is being oxidized and something is being reduced. So before we're going to cover this more in detail, or actually here, but there's a really good slide coming up. But just to cut to the chase, and it just makes sense. So if you remember maybe from high school, but if not, or you're retaking the class, oil rig. So oil rig means it means oxidation is losing, reduction is gaining. And what that means is gaining what? Gaining electrons. So electrons. Now, we'll talk about this more later, but in essence, what happens is in an oxidation reduction reaction, there are two things. One thing is being oxidized, one thing is being reduced, meaning one element, one atom is being reduced and one's being oxidized. Oxidized, meaning it is losing electrons. Where are those electrons going? They're going to the rig. They're going to the reduction part. Reduction is gaining. So you have two things. You have the electrons that are being lost from whatever is being oxidized, and reduction is in the elements or atoms that are gaining electrons. So you're having both of those things happen. So so hopefully we get that. Now, in the oxidation states, there are several rules. Now, if you have an element by itself, meaning sodium solid like this, even if it's a molecule, but it's the element by itself, it's only one element, its oxidation state is 0. And that's because there's no electron movement. It's just sitting there. It's not reacting to anything. There's no charge to it. If you touch sodium metal, you'll be fine. You're not going to get zapped or anything. There's no charge. So Anything by itself is 0. Any monatomic ion is the same as its charge. In other words, all of the ions we know, it's the same rules. So 1A is +1, 2A is +2, aluminum is +3 and 3A, gallium is +3, the halogens are -1, things like that. So fluorine is always -1. That's kind of redundant. Oxygen is -2, except when it's in peroxides. Now, there's different types of peroxides. The most common one is hydrogen peroxide. So in this one, I just expect you to know H2O2 is hydrogen peroxide. And in this case, oxygen has an oxidation state of -1. Usually it's -2. And hydrogen is and be able to figure out what's being oxidized and what's being reduced. That's the goal of this section. So once we get into examples, you'll see how easy that is. But right now, I'm just kind of paving the way for that. So as a practice, let's try to assign oxidation